Hello, dear students. Welcome to our channel OnlyPhysics JEE Grad. Today we'll be discussing JEE Advanced PYQs, JEE Advanced PYQs from the chapter Dual Nature. This will be the third video on this chapter, and the topics will be covering our X-ray. Okay, and this will be the last video. So this will be the last video on this chapter, Dual Nature, and there are 17 questions which we will be covering in this video. So let us start with our first question. Perfect. So this is our first question. Now it is given that lambda of copper is the lambda cu is the wavelength of K alpha X-ray line of copper whose atomic number is this, right? And lambda mo, it must be molybdenum. Its atomic number is 42. Okay, and then we need to find the ratio of this. So we'll use the Moseley's law. It is root of frequency is equals to a z minus sigma, right? And for k alpha, sigma we take it as 1, right? So let's start. And the frequency we can write it as c by lambda, right? So we need to find for the copper, and this will be A is constant, right? So this will be Z of copper minus 1, and we need to divide it with, okay, so let's take molybdenum, molybdenum on the numerator, okay, and this will be, so it does not matter, let's take them, we'll interchange it in the later stage. So it should be divided by A, it will be ZMO minus 1, right? So we'll get lambda MO upon lambda of copper to the root will be equals to Z of copper. So Z of copper is 29 minus 1, 28 divided by, this is 42, 42 minus 1, 41. So if you take the square of this, it will be M lambda MO upon lambda of copper, it will be 28 upon 41 square, right? And we need to interchange it, so it will be lambda of copper upon lambda of m. It will be 41 upon 28 to the whole square, right? So if I use the calculator really fast, it should be near to 2, right? Let's check. 41 into 41 divided by 28 and 28. So the exact answer is 2.144. Yes, so B will be the option. Okay. So quite an easy question it is. Let's move on to question number second. Let's move on to question number second. Right. Perfect. So we have which one of the following statement is wrong, okay, in the context of X-ray generated from X-ray tube. Okay, perfect. So wavelength of characteristics X-ray decreases when the atomic number of the target increases. Yes, so this is correct, right? We know, look here, is from the Moseley's law. The relation is 1 up c upon lambda to the root will be equals to a z minus sigma. So if z increases, this whole increases, so lambda should decrease. So this A statement is correct. All right, so this A statement is correct. Let's check B option. So cutoff wavelength of the continuous X-rays depends on the atomic number of the target. So this is wrong, right? Because cutoff depend on the potential difference. We write EV is equals to HC upon lambda, right? So the lambda is inversely proportional to potential difference, right? So B will be the option because this is incorrect, right? Let's check C. Intensity of characteristics X-ray depends on electrical power given to the X-ray. Yes, so this is correct because power is directly proportional to intensity. If you increase the power, the number of electron will increase and hence intensity of X-ray will increase, right? So this C option is correct. Now let's check the D option. So cutoff wavelength of the continuous X-rays, right? Continuous X-ray depends on the energy of electrons in the X-ray tube. So yes, this is correct again. That is what we have written here. So definitely cutoff wavelength depends on the energy of the electron, not on the atomic number of the target, right? So B option is correct. Let's move on to this third question we have. So let's move on to the third question. Perfect. So electron with the de Broglie wavelength lambda fall on the target in an X-ray tube. Perfect. The cutoff wavelength of the emitted X-ray. So look, in the like in the flow we can write, as we know electron have a wavelength lambda, so due to energy conservation and blah blah blah, X-ray must have the same wavelength, right? But this is incorrect, right? Look, we need to solve it. If the answer come lambda equal to lambda naught, that's fine, right? So let's check. So we know the de Broglie wavelength lambda will be equals to h upon p, and p we can write it as 2mk. So k is the kinetic energy of the electron, right? Now we need to find the wavelength of X-ray. Okay, we know the kinetic energy of electron must be equals to the energy of the photon, right? Because electron is going to lose all its energy, and hence so wavelength will get, right? So let me write it as lambda ph. Okay, so here from here we can write, we can put the value of k here, right? So if you find, so k will come out to be h square upon lambda square upon 2m, right? So it will be here k. Let's put it here. So h square upon lambda square into 2m is equals to hc upon lambda ph, right? Right? Are you getting me? H1h will get cancelled, so lambda ph will get c lambda square 2m. So 2m lambda square, okay, divided by 1h will be here, right? Everything is correct. So yes, this will be the answer. Are you getting me? 2mc lambda square upon h. Perfect. Right? Now you must be asking, sir, why it is happening? Why it is happening over here? So look, electron cannot move with the speed c. That is the problem here, right? Whereas our photon, it is moving with the speed c, right? So if electron is moving with the speed c, then definitely lambda naught will be equals to lambda, right? But it is not happening. Are you getting? So that is the issue. Let's move on. So actually we don't know, of course, if this electron is moving with the speed c or not. That is why we have put lambda here. Okay. So let's start. Let's move on to our fourth question now. So this is our fourth question and fifth question. So in the fourth question we have K again, Ka wavelength emitted by an atom of atomic number Z is given, and lambda is it is lambda. So we need to find the atomic number. So this is again question based on Moseley's law. So we'll write simply C by lambda will be equals to A, and Z is 11. So 11 minus sigma. Sigma is 1, right, for K alpha. So divided by C upon 4 lambda, it is equals to A, right? We need to divide them. Z we need to find, and it will be 1, right? So this will be simply 2 equals to A will get cancelled, and this will be 10 on Z minus 1. So this will be 5. So Z will be 6. Okay. So again, quite easy question. A will be the option. Let's move on to our first question. So we have potential difference of X-ray tube is this, current is this, then the number of electrons striking the target per second. So we know current will be equals to charge moved per unit of time, right? So Q will be equals to, as there are electrons, so we'll write N E upon T. So we need to find N by T. So N by T will be equals to I by E, right? So I we know it is 3.2 into 10 raised to power minus 3 divided by E we know 1.6 into 10 raised to power minus 19, right? So this will be 2, and this will be what? 19 minus 3 is 16. So 10 to, so 2. So answer will be 2 into 10 raised to power 16, right? So A will be the correct, right? Okay, so this potential difference we don't know. It is if it asks that what will be the resistance of this accelerator, then we can definitely find it. But right now it is not needed. Let's move on to our sixth question. So this video will be very short. Okay, this will be video will be very short. Okay, perfect. So this is our sixth question, right? Let's start. So we have intensity of X-rays. This is I from the college tube. It's plotted against the lambda as is shown in figure. The minimum wavelength found is lambda c. Okay, so lambda c will be equals to hc upon kinetic energy of electron, right? And the wavelength of k alpha line is lambda k, right? So lambda k, so 1 by root lambda k. So c by root lambda k will be equals to a z minus 1, right? Okay. Now, as the accelerating voltage is increased, so voltage is increased, so kinetic energy of electron will increase and lambda c will decrease. Okay, and lambda k will remain constant because it is a materials property. Characteristics wavelength is materials property, right? So it says lambda k minus lambda c. So lambda k minus lambda c. So this is constant, and if decreases, this decreases, this whole value increases. So A option is correct. Okay, so A option will be correct. Other options, so this decreases wrong, increases, so these are wrong. Lambda k will be the constant, it is a materials property. Let's move on to 184, which is our seventh question, right? So let's start. Electron with energy this are incident on tungsten target. Okay, so the kinetic energy of electron is 18 kilo electron volt, right? K shell electron of tungsten have 72 kilo electron volt. So look, so K shell, the energy of K shell, right? Electron is 72.5 kilo electron volt, right? So look, this kinetic energy is greater than Ek. Okay, so let me make the diagram for you. So we have a nucleus here, right? So this is our nucleus and these are our electrons. Okay, right? And so on and so forth. Now what will happen is, look, these electrons, there will be a lot of electrons here. Okay, are you getting me? Now if an electron comes, if an electron comes with this energy and it strikes this, right? So this electron requires how much? It requires only 72.5 and we have 80 kilo electron volt. So what happens is there can be many situations arises here, like the left energy. So how much is the left energy? It will be 7.5, right? So 7.5 maybe is given to this electron, or maybe this electron takes it, or maybe photons will release, right? So we'll get like a continuous spectrum. Okay, are you getting me? And we also get we also get a minimum wavelength, right? So how much that minimum wavelength it will be, right? It will be according to kinetic energy of this electron, right? So let's first find the minimum wavelength. So lambda minimum will be equals to, of course, like no energy is given and this electron loses all of its energy and it releases a photon, right? Okay, so there will be no emission of k alpha wavelength, right? So it will be Hc, so 1240 upon 80,000. So this will be nanometer, right? So if I use the calculator really fast, we'll get 1240 divided by 80,000. So we'll get 0.0155 nanometer. So it will be 0.155 angstrom, right? So this will be the minimum wavelength which is possible. And after that, there will be a lot of wavelengths, continuous spectrum will be there. And also K alpha K alpha will also be there. Means continuous X-rays will be there with minimum wavelength. Minimum wavelength of photon will also be there, whose wavelength is 0.155, and also there will be characteristics X-ray will also be there, because the kinetic energy is more than the K shell energy, so all the electrons can be released. Okay, so let's check. So continuous spectrum, Bremsstrahlung long with minimum wavelength of 0. So this is correct, right? Now a continuous X-ray spectrum with all wavelengths. So this is wrong, right? After these wavelength, there will be there. The characteristics X-ray spectrum of tungsten. So this is also correct. A continuous X-ray spectrum with minimum wavelength this and the characteristic X-ray spectrum of tungsten. So yes, D option is the most correct among them. So A and C are also correct, but D is the most correct. Okay. So this question is quite interesting. Let's move on to 185, which is this was our seventh. So this is our eighth question. So K alpha is given, lambda is given, the energy between K and L levels in this atom is about. So this is simple, right? We have n equals to 1, this is n equals to 2, this is n equals to 3, right? So this is K alpha, right? So this is K alpha, right? So we can see simply the energy will be equals to hc by lambda. So lambda will just put, so 1240 upon lambda will be 0.021. So this will be electron volt. Let me use the calculator really fast. So it will be 1240 divided by 0.021, right? So it will be approximately 59047.6 something, right? So you can write it as 1, 2, 3. So it will be 59 kilo electron volt, right? So C is the correct. Okay, let's move on to our next question, which is 9. Perfect. So this is our ninth question. Okay, this is a slight interesting question we have. Let's check. Now, in an X-ray tube, electrons are emitted from a filament, okay, carrying a current I, hit a target at a distance t from the cathode. So we have anode here, right? And we have cathode here. And the distance is given, so it is d. So it must be theoretical, I don't know. Now let's check. The filament cathode carrying a current I hit the target. So of course electrons are released from cathode and these are carrying current I. So like we can say the current is I. Okay. Now what happens is the target is kept at a potential difference V higher than the cathode, resulting in the emission of continuous and characteristics X-rays. Okay. So the potential, so there is a V potential difference, right? Now if the filament current I is decreased to I by 2, okay, the potential difference V is increased to 2V and the separation is reduced to D by 2. Okay, so what will happen? Let's check. Okay, so this current I, okay, this is the current and is the filament carrying current. Okay, so look, this is not I. We're talking about here. These electrons are carrying current I. Okay, perfect. Now this current becomes I by 2. This D becomes D by 2 and this V becomes 2V. Okay. Now look, if the current decreases, that means number of electrons reaching at the anode decreases. So intensity will definitely decrease. So intensity will decrease. Okay. Now intensity decreases. Now look, this potential difference becomes 2V. This potential difference becomes 2V. So the kinetic energy of electrons increases. So kinetic energy of electron increases. That means the cutoff wavelength will decrease. So if this becomes 2V, so cutoff voltage, new cutoff voltage, let's call it lambda cutoff, it will be lambda cutoff divided by 2. So it will become half. Okay. Now this d by 2, there is actually no effect. So this distance decreases. Due to that, this might be happening that this potential is increases. Eventually, look, the potential difference is actually 2V. So we don't need to care about this d, right? So these are the result. The intensity will decrease, lambda will decrease. Okay. Now what about the characteristics X-ray? Characteristics X-ray. So characteristics X-ray depends on the atomic number of the anode material. So it will remain same. So let's check the options. So cutoff wavelength will reduce to half, right? And the wavelength of characteristics will remain same. So A is correct, right? Next, B option. The cutoff wavelength as well as wavelength of characteristics will remain same. This is wrong. Cutoff will decrease. Okay. The cutoff wavelength will reduce to half, correct? The intensity of all X-rays will decrease. Definitely they will decrease, right? Because this current decreases. So this is not the I current. So it's a filament current, the current between the filaments. The cutoff wavelength will become so 2 times larger. This is wrong. So A and C will be the correct option, right? Now let's move on to question number 10th. So let's move on to question number 10th. We have now the X-ray are produced in the X-ray tube operating at a given accelerating voltage. The wavelength of the continuous X-ray has the values. Look, the value we know the continuous X-ray should be lambda minimum to infinity, right? So there is a minimum wavelength which is produced, which is equals to hc upon ev, right? And from there the infinite wavelength can be up to infinite, right? So which option is correct? 0 to infinite, A is definitely wrong. 0 to lambda max, so 0 should not be there. Now B option, lambda minimum to infinite, where lambda minimum is greater than 0. So this is correct. B is correct, right? C, lambda minimum to lambda max. So look, there is no upper limit to the wavelength. So the D option is correct. So it can be up to infinity. So there is no limit of the wavelength which is going to release. Okay. So it says there is a limit of lambda max. So there is no limit. So B option is absolutely correct. Okay. Quite interesting question. Let's move on to our question number 11th. Right. So let me zoom in a bit. This is our 11th question. So potential difference applies to X-ray tube is increased. Of course, lambda minimum wavelength will decrease, right? So D option, right? So D option will be there. Okay. The minimum wavelength increases, so B is absolutely wrong. A, the intensity increases. So will there be effect on intensity? No, because the intensity depends on the number of electrons which are reaching our anode. So there is nothing given. So we'll consider intensity to be constant. So intensity to be constant. C option is correct. Okay. Let's move on to our question number 12. So X-ray beam coming from an X-ray tube will be monochromatic. This is absolute wrong, right? Having all the wavelength smaller than certain maximum wavelength. No, there is a cap on minimum wavelength. So having all wavelength larger than a certain minimum. So this C is correct. So A is wrong, right? C is correct. having all wavelength lying between minimum and maximum. So this is the absolute same question which we have just discussed. So this question is the both are the same question. Okay. Now let's move on to 13th question. The shortest wavelength of X-ray emitted from an X-ray tube depends on the voltage applied to the tube. So B is correct, right? Current on the tube, that is wrong. It depends on the voltage. Nature, again same. You will say, sir, voltage and current is same. No, that is the wrong, right? Look, if this is our tube, this is our college tube, right? So it is like this, right? And this is the potential difference we have applied. Now look, there is an I1 current here and there is an I2 current here. So current can be different here. Okay, this V is the potential difference between these two. Are you getting me? So it is asking current in the tube. Okay, so this I2 and this V, they don't have any like at such relationship. Okay, so we'll just consider the voltage applied to that. This A option is wrong. The nature of the gas, definitely not. The atomic number of the no. So the atomic number, it is the characteristic wavelength which depends on the atomic number. Okay, so we are talking about shortest wavelength here. So shortest wavelength will only depend on the potential difference applied between the filament of the tube. Okay, let's move on to our question number 14th. Right. So this is 14th, this is 15th, 16th, and 17th. Okay, last four questions. First, if the accelerating potential difference, let me zoom in a bit. Okay, perfect. So, if the accelerating potential difference in the X-ray tube is increased, so if we increase the wavelength of the characteristics X-ray do not change. That is right, absolutely right. Because characteristic X-rays depends on the atomic number of the material, right? According to Moseley's law. When an electron beam strikes the target in the X-ray tube, part of the kinetic energy is converted into X-ray. That is we called continuous spectrum we get, right? So this is correct, but they do not explain each other. So B will be the correct option, right? Let's move on to our 193, which is 15th question. So a potential difference of 20 kilovolt is applied in the so minimum, so this is quite simple, right? So it will be 1240 divided by 20,000, right? So it will be 620 and 10 will also get cancelled, so divided by 1000, so it will be 0.062 nanometer, so it will be 0.62 nanometer. Okay, 62 angstroms. So it will be 6 angstrom because we need to find it in angstrom, right? Let's move on to our 16th question. So we have in an X-ray tube accelerating potential 15,000 volts strike copper target the speed of X-rays inside the tube. So it will be the speed of light, which is 3 into 10 raised to power 8, because these X-rays are electromagnetic waves, so speed will be same. If there is a material in a tube, then we can definitely see that the speed will be c by mu, but nothing is given, so we'll just consider it as a speed of light, which is 3 into 10 raised to power 8 meter per second. Okay, let's move on to next question. When the number of electrons striking the anode in the X-ray tube is increased, then dash of the emitted X-ray increase, so it will be the intensity, right? So it will be the intensity. While the speed of electrons striking the anode are increased, the cutoff voltage of emitted X-rays will decrease. Okay, so this is quite easy question. So look, the questions from X-rays are pretty easy, nothing to worry about. Only the one Moseley's law is here, there. right? You just need to learn that, and the picture will be clear. Okay, so be careful while solving. Of course, there can be conceptual mistake while solving this question, but until that, otherwise that, everything is easy. Okay, so this was the last video on the dual nature. We'll meet again with more videos. Thank you.